Yeah, it was a big move for me to go from Switzerland to Seattle, go from academia to industry, and so let me show you the reason why I did that. And the reason is related to HPC. When I had to choose 30 years ago my master's thesis topic, there was one topic where I could use a Cray XMP supercomputer. And then I chose that topic no matter what it was about because I wanted to use that Cray. Now the second day, we realized that the problem they wanted me to solve was one of solving quantum systems. And as Jay mentioned, the problem with quantum systems is there can be negative probabilities. So I failed at my master's thesis because no supercomputer in the world can do it. And over 30 years, I became so frustrated that I said I have to help someone build a quantum computer because that's what I really need to finally finish my master's thesis before I retire. And that relates also to a question asked a few years back by Paul Messina from Argonne about enabling technologies for beyond exascale computing, where he said that this is not just a system that can do more than 10 to the 21 flops, but is something that can do totally new things that we can't even imagine a standard computer doing now. So it's the much anticipated phase change to something truly new. And quantum has the potential to be that. And so it will not replace the classical machines, as Jay said, but it will let us do new things that we don't even think about yet. And that's a problem also for the business side. We're not replacing some business or changing it. We're creating new business, and so it's much harder to estimate how big the market, for example, will be. But the big change here is that when you go back to the old ancient classical computing like abacus, there's not much difference between that and the latest CMOS chip. They all are based on classical binary logic. With the quantum computer, the changes for the first time is not just zeros or ones, but it can be 0 and 1 at the same time. With that, we can solve problems that are classically intractable, like factoring this number. A classical computer for that would take about 1 billion years. Now, when you make it faster by factor 100, it still takes 10 million years. But on a quantum computer with about 4,000 qubits, we can solve that in minutes. So we can solve problems that we just cannot dream of solving classically now. Of course, don't worry about that. We are not interested in breaking crypto because we don't think that's a market. But worry about if you send data around now that you want to stay confidential for 25 years. That will be broken if you use RSA. Also, if you have bitcoins, once somebody has a quantum computer with 2,330 qubits, one can break the Bitcoin encryption, and that way one can steal all your Bitcoin. To make it safe, Microsoft and others are working on new quantum safe, post-quantum crypto, new classical schemes that are not vulnerable to quantum attacks. I think before we have that size machines, we'll update our crypto systems to keep the e-banking, for example, safe. But so what we look for is the applications in fields like in chemistry, catalysis, for fertilizer production, carbon capture, the new materials, superconductors, new dyes, and we have big hope for quantum being a game changer also for machine learning. The first 3 parts we know exactly what to do. The machine learning is still more of a research problem. In order to solve these problems, we don't want to just build a small toy system, but we want to develop and deploy a scalable commercial quantum system to solve today's unsolvable problem. That goes back to the Messiah's question of what can we build that can solve problems that we just cannot ever solve classically. And so that's the goal. That's what we target. To do that, we use the new type of the qubit, the logical qubit. Microsoft built up a big team. They hired not only me, but also your colleagues in Sydney, in Delft, in Copenhagen, Purdue, Santa Barbara, and the center is in Redmond, so it's pretty spread out. As we talked at lunch, this makes it a challenge to find a time when all people can talk on a Skype call. We also work on the full stack, not just the qubit, but the full stack from the qubit up to the control software, hardware, to the classical control software, and the quantum applications, chance libraries, compilers. The qubits we build are based on solid state materials, and so like those of IBM, Google, Rigetti, and others, they have to be cold. So we put them into a cryostat, which is a big fridge, and cool them down to 15 millikelvin, which is more than 100 times colder than deep space. Now, when you put 1 million qubits there, then I do not want to feed in 1 million lines from room temperature to control them. So I want to place the control logic in the cryostat itself. For a small device, we can place it outside, and when you go to a quantum lab, they have racks of equipment next to the cryostat. We need to move all of that into the cryostat and make it get 100 or 1,000 times bigger, while only being able to use a few watts of power. That needs a big effort in engineering here, and then just like in the classical world, software is also a big challenge. So we work on the full stack here. Let me go back to one of John's slides this morning. We said we need both quality and quantity, and he showed nicely how as you make the quality of the qubit better and better, you need fewer and fewer qubits for the error correction. And so the approach we've taken is that instead of taking noisy qubits, and we have lots of qubits that we could scale up, we first want to go to better qubits. Because when you go to better qubits, then you can do much more immediately with fewer qubits. Once we have very good qubits, then we want to scale up. So with the analogy to the classical world, instead of building an exascale machine from vacuum tubes, we first want to invent the transistor and then start scaling up. And that will then reach the goal. The way we do it is we use a so-called Majorana fermion. This is a particle predicted by Troyer Majorana in the 30s. He wrote a paper on that. Then he boarded a ferry to Sicily and was never seen again in the world. His particle, at least, we found in our lab in Delft after this signing the device where it should show up. And I want to quickly give you the idea and why it's challenging. The problem is when you have a particle sitting here, and it could be 0 or 1 electron. I can easily detect that by just measuring the charge. And then the wave function collapses. It becomes either 0 or 1 electron. So what we do is we take this electron and we split it apart into 2 Majorana particles. Or we take 0 electrons and also split it apart. So now we have 2 Majorana particles separated, and jointly they either form 1 electron or not. But if I look just at one of them, then I cannot tell. So local noise will not disturb me, but I have to look at the whole system. I need to bring them together again to find out what it is. And so that way we protect the qubits much better than standard ones. And we want to build that in the devices here based on the nanowires, where we basically split the electron apart in space. That's work in progress. We've seen the particles. We're now building the qubit based on it. In order to build it, the way it makes things better can be compared also to ways of storing classical information. When you draw lines with chalk on a blackboard, then it's safe until you have a storm and it wipes away your chalk marks. But the Incas already found the crypto system where they used knots and strings to store information. And that you can shake around, the string can get longer and shorter. Noise here with knots does not matter because the knots are the topological property that is more robust to noise. And this same idea is used in the qubits. To make the qubits again, we use HPC modeling. So that's another link to HPC. But now let me come to the top of the stack, the software and the applications. Because that's where we have to spend at least as much time as on the qubits and the control. We were already shown by Jay that it's wrong to say quantum computers are fast because they operate on all values simultaneously. The quantum computer does that some way, so you can create the superposition of states, which is like working with an infinitely big SIMD register, vector register. But while I can calculate on the superposition, if I then want to read it out, quantum mechanics only gives me randomly one of the values. And I have not gained anything compared to doing the calculation starting with a random input. So in order to get something out, the important step is then we have to do some kind of reduction operation to reduce this big superposition back to one of a few values only, where when I then read out one of them randomly, it still gives me the result. And the big challenge here is finding the quantum algorithm that does this reduction. This is magic here. And not just that we do things in quantum parallel. And that's why there are just few quantum algorithms yet. It will not just replace any classical code. So to develop a quantum atom application, I first find such a quantum algorithm. And there's a big list of them on the NIST webpage, the quantum algorithm Zoo, maintained by Stephen Jordan. And he made a big list of all the known quantum algorithms. So that's the starting point. You pick one that's useful for your problem. But then we have to do a few more things. Next, we have to confirm that there's still quantum speed up, that it still scales better than a classical algorithm after you've implemented all of the algorithms, including the I/O. One example is Grover search. You can accelerate database search quadratically on a quantum computer, as long as you don't take into account the cost of loading that database when it's the real one from memory. Because you always need to load it, and while you load it, you found the data. Then, after you check the speed up, we have to check that the code, when we implement it and run it, has a runtime that is not just asymptotically faster than a classical one, but also for a real problem. And we found many cases where the quantum computer has exponential speed up over classical ones, and it will be better than a classical computer once you have a calculation that takes about the age of the universe. When the calculation should take even longer than the quantum computer wins. We need to bring that down to days or weeks. So we need to really work on the code and make it faster. And then at the end we have to run it somewhere and check that it still works. And for that we need a new group of people who are quantum software engineers who we have to train. To do that, we released the Microsoft Quantum Development Kit. It's a quantum programming language, Q#, which is the high-level language. I do not want to write my code in assembly. I don't want to write an adder by using NAND gates, classically, and not quantumly. I want to write it at the high level of the abstraction. I just want to call my quantum algorithm. The Q# lets you do that. We integrated it into Visual Studio. It comes with your couplings to C#, C, Python, C, Fortran. If you want to, it runs on Windows, Mac OS, and Linux. It comes with the simulator and with an extensive open source library of samples and quantum algorithms. I want to look a bit at the backends. It comes with the free simulator that runs locally, lets you simulate as many qubits as you have memory in your machine. When you have 16 gigabyte, that is your 30 qubits. If you want to do more, we have a distributed simulator in the cloud that can do 40, 41, 42, 43 qubits. You can do more if you're willing to pay for bigger clusters. We have a tracer that gives you the runtime for when you have the big programs that won't fit. And we can also target your future quantum computers. Since this is about HPC, I want to mention a bit about the distributed simulator. The first version was written by my students. They ran it last year on the Core 2 system in Berkeley and managed to do 45 qubits. Compared to the simulator that was mentioned this morning by Intel, this one reduces the network traffic by about the factor of 30, and thus is much faster. There's also no need to buy a machine. There are vendors out there they sell you a special purpose here, so the supercomputer that can do the 40 qubits. With us, you don't need that. We give you the cloud access to bigger ones. Now, in the last couple of minutes, I want to mention one of the things that we can do with it and why it's important to really think about the software. One of the clear applications is that we can use quantum computers to solve quantum physics problems, like problems in chemistry, material science, nuclear physics, particle physics, and so on. These are exponentially hard classically. They're much easier on quantum hardware. But when you look at what it takes, and I look at the problem, and I go to about 100 orbitals, which is the problem size that is classically intractable, then the first quantum algorithms that were out there would have taken about 24 billion years to solve a certain benchmark problem. Yes, it's classically intractable, but this is not very encouraging. So then we sat down and improved the algorithms. And over 3 years, we brought it down to days, hours, minutes, the time. When we simulated, we find that actually it runs even faster than the bounds we have. And so we can do things in minutes now, which before would have taken years. And that just shows you how much you need software improvement also for quantum computers. We then applied that to one problem, the problem of understanding the process of biological nitrogen fixation. This is the way of making a fertilizer with less resources than can be done now. We showed that this works. Let me just come to the main point of that. Is it only needs about 109 qubits. But we need good logical qubits. And we need to run the calculations in parallel, making rotations and so on nicely in parallel. When we then cost out how big a machine we would have to build, then we get scared. So we find if the error rate is 10 to the minus 3, then we would need about 5 billion physical qubits to solve this problem. But if the qubits are better, if the error rate is 10 to the minus 6 or 9, then we only need about 30 million or 5 million qubits. That looks much more feasible. And so what that shows us, we need to really go for better quality qubits. We need to still work on better algorithms that bring the cost down. We need to work on better quantum error correction. And just last year, the group made the breakthrough, and now all these numbers are down by a factor 50 already. And we hope in the next years we'll bring it down by another factor 100 or more. So what that shows us is we really need to start working on the software and not just the hardware. And I invite you all to work on that, to download the Microsoft Quantum Development Kit and start writing quantum programs to be ready for the time when we have the quantum hardware. Thank you.